Okay, good evening everyone. Welcome you all to this NPTEL course entitled Study Guide in Organic Retrosynthesis Problem Solving Approach. So this is the last week of tutorials. So myself Anirban Maiti from IIT Bombay Department of Chemistry, and the course instructor for this course is Professor Somik Nanda from IIT Kharagpur. Okay. So coming to the synthons and synthetic equivalence, so we have talked about the synthons and synthetic equivalence. So whenever we will break any carbon-carbon single bond, that time, like heterolytic cleavage, if we are thinking that time we can get donor synthon and acceptor synthon. Okay, donor synthon mean that carbon. So this carbon will take two electrons from this bond, so this will get negatively charged and the other carbon will get positively charged, right? So the negative charge, so that can donate its electron. So basically, so it's known as donor syntone, and other carbon which is positively charged, so that can accept the electrons, so that's why it is acceptor syntone. So now among these donor syntones there are various examples of donor syntones, and also corresponding to that synthetic equivalents are also there. And so which reagent we have to use for particular donor syntone, that also I have written here. Okay, so this already we have discussed. Similarly, acceptor syntones also various, like alkyl cation, acylium ion. So many acceptor syntones I have written. Yeah, and corresponding to those acceptor syntone I have written the synthetic equivalent. Okay. So that is the case. Now now I'll go to examples. So this is the examples where you can see. So where you can see is this aromatic ring is there, and two hydroxy group is there, both are tertiary alcohol. Okay, so how we can plan the retrosynthetic analysis for this molecule? Can you please write down in your notebook, or can you please comment on which CC bond or CO bond we can disconnect? Just write in your notebook, then I will show you. Okay, let's see. So there are two hydroxy group, right? So first we can have this CC bond disconnection. Okay, this carbon carbon and this carbon carbon bond disconnections. So as this is a tertiary alcohol, so we can think of ester from where this alcohol is coming, and if you add two equivalent of Grignard reagents, then we will get this compound. Okay. So if we add two equivalent of Grignard's reagents, then we'll get this target molecule. Now from where we can get this alpha hydroxy ester. So let's see. So we can get from this ketone, compound ketone. So how we'll get? So that we will see in forward synthesis. And this ketone, yeah, this ketone also we could get from this is the aromatic ring. This is chlorine. Yeah, from chlorobenzene we can get this ketone via radical acylation reaction. Okay, so let's see in forward synthesis how we are doing. So first we have to treat, we have to take this chloroacetone, sorry, chlorobenzene, and then if we treat this chlorobenzene with this, oh yeah, so how we'll get this compound? How we'll get this compound? So basically you have to do Friedel-Cap acylation reaction, and we'll get the corresponding compound. And this is the chloro acetyl chloride with aluminum trichloride that we will use as a Lewis acid. So basically we will get this compound. Okay, and then yeah, sorry, yeah, then from this compound, how we will get this compound? So basically, this is the if you see this compound, so alcohol we are getting here, and cyanide addition we can do. Okay, so basically, if we add cyanide into this ketone, we will get this alcohol. Okay, cyanohydrine. Okay, and by using casein potassium cyanide or sodium cyanide is more good. Yeah, so after getting this compound, we will treat it with this H2SO4. So hydrolysis will happen of cyanide, and it will give uh, this amide. Okay, this amide it will form. Now again hydrolysis, basic hydrolysis, it will give this acid. Okay, this corresponding acid. So cyanide hydrolysis to acid with first with acid, then base. Okay, so we'll get this carboxylic acid. Okay, and then if we do this esterification with methanol in presence of mineral acid, we'll get the corresponding ester. Okay, so after getting this ester, what we have to do? Basically, we need to add two equivalent of Grignard's reagents to get the corresponding tertiary alcohol. Okay, so this methyl magnesium iodide we have to use two equivalent, and we will get direct this tertiary alcohol, right? So this is our target molecule. Okay, yeah, okay. So now, okay, now we will see some. So these are the examples with small molecules retrosynthesis. Now we will see some retrosynthetic plan for little big molecules. Okay, some more complexity with some more stereochemistry. We will see some of those examples. Okay, I have taken directly from journals. So chemistry Asian journal paper. So they have published the asymmetric synthesis of this plus febrifugin. So this molecule, if you see, so it was isolated. So this is the natural product. Okay, so this natural product was isolated in 1947, during 1947 to 1950, from the traditional Chinese herb named Dichroa febrifuga. Okay, so and this molecule, what is the biological activity for this molecule? So all of we know for anti-malaria activity, so quinine is responsible for anti-malarial activity, or to treat to treat malaria we need to use quinine as a drug. Okay, so there is this febrifugin also, an natural product which shows, as you see this second bullet point, so this is having 100 times greater anti-malarial potency than the quinine drug. Okay, so this is the quinine. I can write the structure of quinine. It is a bicyclic compound. So first is quinine ring. Okay, So this is the quinoline ring. Here nitrogen will be there. This is nitrogen, okay. And here at this carbon, O methoxy. And at this carbon there is vinyl group, okay. And this carbon having alpha hydroxy group. So this is the quinine. So this molecule, the name of this molecule is quinine. That is also a natural product. So that is cinchona alkaloid, isolated from cinchona species or remigia species. So this is the alkaloid. So all of we know this quinine is very much important for anti-malaria activities. Okay, so but is plus febrifugin also an antimalarial agent which is having 100 times greater antimalarial potency than this quinine natural product, okay. Also this febrifugin also exhibits potent antimalarial activity against both chloroquine sensitive and chloroquine resistant p falciparum by inhibiting prolyl transfer RNA synthesis pro-RS, that is pro-RS activity, okay. So this is the biological importance of this natural product febrifugin. And now we will see the retrosynthesis for this molecule, okay. So if you see this molecule, so this part is quinazolinone unit, okay. So this part is quinazolinone unit, and this right side part is substituted piperidine ring. So this is the six member piperidine ring, and now these two carbons are substituted, okay. So this is the plus fabric fugin. Now how we can plan the retrosynthetic approach? So what will be the correct retrosynthetic approach, okay. So first we can think this quinazolinone fragment and this compound 2, okay. So this we can get like this. If we couple these two fragment, then we will get this plus fabricugin. Basically this carbon and this nitrogen, this bond formation we have to do, okay, in forward synthesis, sorry. So this carbon and this nitrogen, this bond we have to make, okay. So in forward synthesis we'll see how we are making this bond. Now, okay, so now this quinazolinone is okay, that is commercially available. Now this fragment 2, so this fragment how we will get? So basically we can get via this cyclization, okay. This cyclization reaction we can get, okay. So this NH and this, if you see, this is six member ring. So basically 1 2 3 4 5 6. So this N and this C bond, okay, we have to make, okay. So then we can get this six member ring, okay. So basically if we do lactamization, then reduction of this lactam, we'll get this six member ring, okay. So this we can get. Now this molecule compound 3, how we can get from 4 via HWE olefination between this aldehyde and this right side fragment. So Horner Wordsworth Imon olefination, HWE, basically Wittig reaction we have to do between this aldehyde. So this is the aldehyde, this carbon is from this aldehyde, and this part we have to take from this Wittig reagent, okay. 1 minute. So basically, sorry. So this is the CO2 ET, and this is the PPH3, right? So we have to do ET reaction. So if we do HWE olefination between this Wittig reagent and this aldehyde, we will get this compound 3, right? Any doubt? No doubt, I guess. Okay. Now this compound 4. So compound 4, if you see, it is having two stereo center. Okay. So this one and this one. Okay. So basically, we have to take from any chiral chiral building block. So we can think about this compound 5. So this 4 we could get from compound 5 via this zinc mediated Barnett Vasella reaction. Okay, so this is a name reaction. Scientists Barnett and Vasella, they have developed this reaction. Like this is a sugar ring. Okay, this is a sugar compound. Okay, so this sugar compound. So basically, if we treat this with zinc, we will get this olefin. Okay, so basically, I will for discussing forward synthesis how it is happening. Okay, now this compound 5 we could get from 6 or 7. Okay, so let's see, let's discuss this 6 how we can get. So this 6 basically, if we do reduction of this azide, we'll get NH2, then we can protect this NH2 to NH box. Okay, now this compound 6 we could get from D glucose. Okay, also we could get this compound 5 from 7 where azide is not there. Okay, compound 6 is having azide. Also we can get this compound 5 from this oxime. Okay, instead of azide we can get this 5 from oxime, and this oxime we could get from D glucose. Okay, so D glucose is commercially available, it is very cheaper, we know, and also it is an chiral building block. Okay, so it is having 1 2 3 4, yeah, 1 2 3 4 4 chiral centers. Okay, so this is a commercially available and cheaper, very high, you can easily get from anywhere. So D-glucose is highly cheap and it is an chiral building block. So we could, so you can see how plus febrifugin is targeted from a commercially available chiral building block D-glucose. Okay, a very interesting example. So this forward synthesis, sorry, retrosynthesis. Any doubt? Then you can ask me. Otherwise, I will go for forward synthesis. You can just see and think. Okay, so then I can move to forward synthesis. So D glucose. We have started from D glucose, as we have mentioned here. We are starting from D glucose. It is commercially available. So D glucose we are starting, and we are getting 9. How we are getting this 9? What is D glucose? So D glucose is basically, so this is the D glucose, right? OH, OH, and this carbon having CH2OH. Okay. So total 4 chiral centers are there. So this side is hydrogen. Similarly, this side and this side is a hydrogen, right? So this is the structure of D-glucose. Now this is the acyclic form. Okay, so now it can exist in cyclic form, right? So it in solution it will be in equilibrium with 6 member ring as well as 5 member ring. Okay, now 5 member ring, how it will exist? Okay, so basically first we have to draw the furan ring. If we convert, sorry, if we convert this D-glucose to 5 member furan ring, so it will looks like, I'm just drawing OH. This is a number one carbon, number two, number three is beta, then number four, one, two, three, four, yeah, five, six. So this is the OH, again beta carbon, and this is the CH2OH, and this carbon is beta. Okay, so as you can see, so this is a one number one carbon, mean this carbon, then second carbon, the second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. Okay, so this is the furan form of D-glucose. Okay, now as you see, we are treating this D-glucose with acetone, and paratoluene sulfonic acid, that is acid catalyst acid, and this is the trimethyl orthoformate. So what will happen in acetone? Both 1 to 6 diol, that will get protect. Okay, so basically these two alcohol is cis, both are alpha. It will get protect with this acetone, and these two alcohol also get protected with this acetone. Okay, so it will give this compound 9. Any doubt? If you have any doubt, then you can write in comment section. So this we should know how this reaction is happening. D-glucose to this compound 9 is known as glucose diacetonide. Okay, diacetonide. Acetonide mean this acetone protection of this 1,2 diol. So this is the monoacetonide, and two total two acetonides are there. This is the acetonide, and this is another acetonide. And if you see, this is primary alcohol. Here one alcohol is primary, and here one alcohol, both alcohol are secondary. So we'll call this acetonide as a primary acetonide, and this acetonide as a uh, secondary acetonide. Okay. Okay, so we are getting this compound 9 from this D glucose, right? Any doubt? Okay, no problem. So now this compound 9, first we will see how. So we need to get this compound 10. Okay, first we will see from via agide approach. Okay, via this agide approach, how we are getting this compound 10. Okay, this alcohol, now if you see this condition number 1, triflic anhydride pyridine DCM minus 10 degrees centigrade to RT 30 minutes. Okay, so what will form? So what it will form? So triplet anhydride is there, pyridine in DCM is solvent, and the temperature is minus 10 degree, and it is 30 minutes reaction. What will happen? Yeah, basically what will happen? This triplet anhydride is trifluoro sulfonic anhydride. Okay, so it will form. So this is a like acetic anhydride. Okay, acetic anhydride kind of things like similar chemistry. So basically, this alcohol will attack the carbonyl carbon of this anhydride. Okay, triplet anhydride, and it will form this OTF. Okay, it will form OTF. Now this OTF is living group. Okay, so this OTF we know OTS, OTF, O mesylate, all are living group. Okay, so basically now second step is if you see the reagent is sodium azide and DMF, and the temperature is RT room temperature, and the reaction is for 18 hour. So now in first step we are making this living group OTF. Okay, so and second step if you see this reagent, this is sodium azide. So sodium azide mean Na plus N3 minus, that is ionic, and azide is nucleophile. Okay, so what? So now it's pretty easy. You have living group ready in your first step. Now you are adding sodium azide onto that. Okay, so what will happen? So substitution reaction will happen. Okay, nucleophilic substitution reaction will happen with the sodium azide, and you will get this azide. Okay, so substitution SN2 reaction will happen. That's why if you see the stereochemistry as well at this carbon, it is getting reversed now. That C3 carbon, the stereochemistry is reversed. Okay, so that means SN2 reaction is happening. Now this azide we are getting. Now if you see this yield for this two step is 44%. Okay, for this two step, first and second step, total yield is 44%. To get 9, to get this 6 from 9. Okay, now this azide now we are treating with this PPH3 in THF solvent, then we are adding triethylamine after 1 hour, and what we'll basically get in first step, basically if you have azide and if you treat azide with PPH3, Schrodinger reduction will happen. Okay, that means N3 to NH2 will form. Okay, so the name reaction is known as Schrodinger reaction. Okay, so azide to amine NH2 will form. So it will get NH2. It will give. Okay. Now, okay. So Schrodinger reduction. Okay, you can search if you know want to know the mechanism for this. You can search in Google or any other textbook. You will get easily. Okay, the mechanism. I'll not go into details of mechanism, so rather I will focus on the forward synthesis most. Okay, so first this amine. So this amine, if we treat with Bock anhydride, again this similar to triplet anhydride or acetic anhydride. Bock anhydride mean Bock group will be there. So what is Bock anhydride basically? So this is the Bock anhydride, right? Now, so similarly, what will happen? This amine will attack to this carbon. So this amine will attack to this carbon, and this group will leave. So basically, you will get this protected amine. Okay, by or NH block. Okay, NH block. So any doubt up to this compound 10? Okay, so after getting this compound 10, now the if you see, this is the agile approach where to get this agile we are getting 44% yield from 9. Okay, so this yield is very less. So they want to improve the yield for this reaction. That's why they avoid this agile approach. So rather they have used the alternative pathway to get this compound 10. Oh, so what they did? So this compound 9, what they did first, this PDC, they treat with PDC, acetic anhydride and in DCM. Okay, what will happen in this first step? So what will happen in this first step? PDC is oxidizing agent, right? Pyridinium dichromate. So it will oxidize. Basically, oxidation will happen. So oxidation of what? If you see the starting metal 9, it is having a free hydroxy group at C3 carbon. Okay, so oxidation of that carbon will happen. So basically, this secondary alcohol to carbonyl carbon you will get. So basically, you will get in first step, you will get this carbonyl oxygen. Okay, right. Now in second step, we are treating that carbonyl carbon with hydroxylamine hydrochloride pyridine in ethanol, and the temperature is RT and the reaction time is 18 hours. So what is happening in this second step? Basically carbonyl to oxime formation will happen. Okay, so this hydroxylamine hydrochloride, so this hydroxylamine will add to this carbonyl carbon and it will give this oxime, right? Any doubt? Okay, so this is now compound 7 is converted to this amine via by using molybdenum trioxide sodium borohydride. So first in methanol with 30 minutes reaction. So first what will happen, this sodium borohydride will reduce this CN bond. Now this molybdenum is known to cleave this N oxygen bond. Okay, first in sodium borohydride what will happen, this CN bond will reduce. Now this NO bond, if you see this is amine, okay, so that means this hydroxy group is removed. That means NO bond is breaking. Okay, so how this happening? So that is, so molybdenum trioxide is known for breaking this NO bond. Okay, sometimes people use indium also. Okay, or lithium aluminum hydride also sometimes used. Okay, so here both CN bond is reducing, also NO bond is breaking. Okay, and you will get this amine. Okay, now after getting this amine, we will again we want to get this compound 10. So how we will get, basically the similar step, we have to do the Bach protection of this amine. Okay, so for that we use Bach anhydride methanol in RT for 18 hour. Okay, so we got, now in this strategy, agile free approach strategy, if you check, so here we are getting total 4 step with 68%. So that means it's quite good. Okay, right. Here first two step is 44%. Compared to that, here total 4 step to get this 10 is 68%. So this is the more favorable pathway. Okay, I mean not favorable, I mean more, uh, I mean it's more robust pathway. Okay, so now we can get this compound 10, right? So any doubt in this slide? Okay, so now we'll start from this compound 10 and we'll see. So this compound 10, after getting this compound 10, the similar compound 10, so first we are treating with 10% HClO4. So HClO4 is acid, right? So in ethyl acetate, 0 degree centigrade 1 hour. So what will happen? Basically, it is acid. Okay, acid, in presence of acid. So if you remember, these are two hydroxy group. Okay, these are two one to diol, and it is in protected from. Okay, protect acetonide protection of this. Uh, yeah, acetonide protection of this 1 2 diol, right? So basically, so this protection, deprotection will take place in this first step, okay, in 10% HClO4, okay, deprotection will take place. So basically you will get a removal of this acetone, and you will get 1 2 diol. Okay, so now this 1 2 diol, so NaIO4, so this is known for oxidative cleavage of this 1 2 diol. So and it will give aldehyde, right? 1 2 diol first, 1 2 diol to it will give aldehyde, okay, CHO. Now if you read in the second condition, then they use sodium borohydride, okay. So what will happen? This aldehyde reduction will happen to get this primary alcohol. So first is 1 to diol, then this oxidative cleavage in presence of NaF4, it will give this aldehyde, and this aldehyde will get reduced by NaBH4, right? So you will get this primary alcohol. Okay, any doubt in these three steps? Okay, so after getting this primary alcohol, so what they did, apple reaction they did, okay. Apple reaction mean this alcohol to iodine, okay, by using I2PPH3 imidazole in THF, right? So what will happen? This is the apple reaction, pretty textbook reaction. So alcohol to iodine will form, okay. Now in the second step, so this is the name reaction, is 5. 5 we converted to compound 4 by using this zinc mediated Barnett Bacilla reaction, okay. So these conditions are like sonication. Sonication means sonicator they have to use, or convention condition. Convention mean not just normal reagents and heating in solvents. Some solvents we have to heat it. Okay, that is the convention method. Anyway, the mechanism will be same. Zinc we have to use molecular zinc or zinc powder, molecular zinc in powder form, right? So we have to use. So basically, first this zinc insertion will happen. Okay, so zinc insertion will happen. So I'll write the mechanism for 5 to 4. So zinc insertion will happen between the C and I bond, and it will give this zinc iodine, okay. And now this is the, yeah. So now what will happen? So I am not writing this substituents at this 3 carbon. So I am writing where the reaction is happening, basically reacting. So what will happen first? So this CZN bond will break, and this CO bond will break, and it will give this carbon carbon double bond. Okay, basically what will happen? Basically OZNI will form, and in water it will give alcohol OH. Okay, so you got the mechanism how it is forming. First zinc insertion between the CI bond, then this fragmentation will happen. Okay, so it will give basically this compound 4. Any doubt? And for this condition, for this reaction, okay, they have optimized. Okay, optimized the reaction. So in first condition, zinc THF water mixture. Zinc we need now. The solvent is THF water mixture is 2:1. In sonication, but in sonicator they did the reaction. They performed the reaction, but in 6 hours they did not get any product. Okay, but when they use acetic acid, that time in 0.5 hour they got 43% of product. Okay, so now without sonication they use the conventional heating condition, that is 60-degree heating condition. So in gram scale, yeah, in gram scale, in the same condition compounds with this serial number 2, they are getting this compound with within 1 hour and 49% yield. And for bulk still, they want to get the product. So that time they use ethanol also, and 1 hour 28% yield is they are getting. So this is the more good step, I guess. I like this. Three is more uh, better condition, right? Anyway, after getting this compound 4, so they are doing HWE olefination reaction. Horner-Orsod Emmons olefination. So basically, this is the we take reagent. So the sodium hydride will generate take proton from this carbon. Now this HWE olefination reaction will take place, and it will form this carbon and this carbon double bond. Okay, this carbon and this carbon double bond and this ester. Okay, so compound 3 they got. Okay, so any doubt? Overall doubt in this slide? Okay, then we'll move forward. So we are having this compound 3, right? So compound 3 we have already synthesized in the last slide. We have shown. So now this they treat with TBDPS chloride. That means tart butyl diphenyl silyl chloride in imidazole with imidazole in DCM. Okay. So tart butyl, so diphenyl sorry. So this is the silicon. So this is a TBD paste chloride. Okay, tert-butyl diphenyl chloride. So protection will happen. So this free alcohol is there. Imidazole will take proton. Then this protection OTBD paste protection will happen. Okay. Okay. After getting this compound 12, so what is happening? LiBH4. Okay. So lithium borohydride in THF will get this compound 13. Okay. So this reduction of both ester and this alpha beta unsaturated double bond. Okay. So that will happen and we will get this compound 13. So now this compound 13 we treat with this methyl chloride in triethylamine DCM. Methyl chloride mean MESO2Cl, right? So this free another free alcohol is there in compound 13. So that will make as a O methyl. Okay, mean living group. We are converting this alcohol to living group. So first this OMS will form in first step. Then in second step, sodium hydride THF. Sodium hydride is base, right? So basically, sodium hydride will take proton from this free amine, and now it will act as a nucleophile. Okay, and it will add to this carbon bearing this living group O methyl. So how much member ring will form? So one, two, three, four, five, six. Six member ring will form, and it will give this compound 14. Right? Any doubt in this slide? Okay, so after getting this compound 14, yeah. So this 14 we have now. Okay. Now first, so this side will first check. We'll go first this side. So this 14 we are treating with BH3 boron dimethyl sulfide complex. Okay. In THF cyclohexene and 0 degree centigrade to RT 3 hour then water and sodium borate 4 water. Okay. So what will happen? So hydroboration oxidation will happen, right? All of we know hydroboration oxidation will happen in this carbon carbon double bond, and we'll get basically we'll get hydrogen here and water, sorry, hydroxy group at this terminal carbon, right. So now this hydroxy group in first step we will get, so primary alcohol will get. Now second step is DMP in DCM. DMP is desmethyl para iodine, that is the oxidizing agent. So basically it will oxidize this primary alcohol to aldehyde, right? So this aldehyde will form now. So this is the compound 15. So this aldehyde in situ we are treating with this trimethyl sulfonium iodide in sodium hydride. What will happen? So basically this epoxide will form, right? So this sulfonium iodide, sulfoxonium iodide salt. So epoxide will form, and we will get this compound 16. Now this epoxide ring opening with this 4 quinazolinone. So basically quinazolinone is this one, carbonyl here nitrogen, double bond. This is aromatic ring. So this is the quinazolinone where we are having this nucleophilic amine. Okay. So this NH will take proton, NaH will take proton, and it will give N minus. So that N minus can open this epoxide. Okay. So this reaction is theoretically possible, right? To give this product. Now the problem is that this reaction did not work. Okay. So when we are doing practically, so this is the chemistry. So theoretically, sometimes it will work. Theoretically, you will see that this reaction is pretty easy. It will work, but when you will perform in lab, it may not work. Okay, so that's why we have to do after designing any retrosynthetic analysis, we have to do the forward synthesis in lab. Then if it works, then good, and if it does not work, then we have to move the we have to change the strategy. Okay. Okay, so after getting this 17, they need to do the oxidation of this secondary alcohol and treat with ACl to get this plus febrifugin. Okay, but so this step is not working, so they did not move forward. Okay, so they need to change the like they need to follow some other pathway to get this molecule. Okay, to get this target molecule. So what now they will do? So what plan they can think? Okay, so again similarly first step they are doing this hydroporous oxidation to get this primary alcohol. So same step, first step is similar, right? Now the second step is also same, DMP oxidation to get this aldehyde, right? So aldehyde they can get at this carbon. After getting this primary alcohol in this step, they can get this aldehyde, and now now basically this aldehyde will form. Okay, so this carbon aldehyde will form. So now this second step here in the second step, methyl lithium they are adding. Okay, so methyl lithium mean methyl minus nucleophile. Okay, so basically you will get secondary alcohol OH, and this methyl group, and here according to your substrate, okay, this side. So this secondary alcohol, in the second step we are getting this secondary alcohol, right? So now see the next reagent, and that is also DMP in DCM, right? DMP in DCM. So and the DMP also again oxidizing agent, so desmethyl iodinate. So what will happen? You'll get the oxidation of this alcohol and you will get this compound 19, right? Any doubt up to this 19? So 19 day got, okay, after 4 steps, right? So after that, if you see this LiHMDS mean lithium hexamethyl disilazide. Okay, so basically, so LiHMDS is a base. Okay, so this is N minus Li plus silicon, and this silicon is having trimethyl, and this side also similarly silicon and silicon having trimethyl. Okay, so this is the LiHMDS. Okay, yeah, Li lithium hexamethyl disilazide. So first, what will happen? So LiHMDS will take acidic proton. So this is the two. This is the acidic proton. So it will take this proton and it will give this CH2 minus. Enolate, basically enolate will form. Right. Now, yeah. Now also they are using TMS chloride. Basically, enol TMS will form. Okay, and they are treating enol TMS mean. So this is the enolate will form. First enol O minus, then TMS. Okay, TMS chloride with TMS chloride, it will form this enol TMS. So this will form enol TMS. So this enol TMS, after formation of this enol TMS, you are providing N bromosuccinamide. That means brominating agent. Okay, so basically enol TMS will break, and so it will capture the bromine plus. Okay, and you will get here this Br bond. Okay, so finally you will get at this carbon bromine, right? So now the second step, if you see that quinazolinone, so this is the quinazolinone, right? So quinazolinone K2CO3 in DMF. they use. So quinazolinone. So this K2CO3 will take proton from this quinazolinone, right? So it will form this free amine. So here this N minus will form, right? So this N minus, now this N minus will adds to this SN2 will take place, and this bromine will leave. So basically this carbon, so this carbon and this nitrogen, okay, this nitrogen bond will form, and he'll get this product, okay. So now after that we are treating, so that is the compound. Now if you see this molecule, this plus fabricane is having uh, salt, like chloride salt of this compound, okay. So the last step, what is happening, you are treating this compound with 6 normal HCl in 4 hour. So what basically we'll get in 6 normal HCl 4 hour, we'll get the quaternary salt. So this nitrogen and this nitrogen, okay, it will form NH2 plus Cl minus, and here also NH plus. So two quaternary salt will form of ammonium and Cl minus, okay. So NH2 plus Cl minus, and here NH plus Cl minus, okay. So this will form. Now, so for writing purpose, we can write, like, we can write this molecule and dot 2 HCl, okay. So the same so this means it is in salt form, okay, with chloride salt, quaternary ammonium salt. So that is how they have accomplished the total synthesis of plus fabricane. So very interesting example how we can plan the forward synthesis, and how we can do the, sorry, how we can plan the retrosynthetic analysis, then how we can do the forward synthesis, and then we can get the nasal product in our hand, okay. Very interesting, right? So any doubt in this slide, so then you can write in comment section. Okay, so in this natural product synthesis, so the synthesis of this plus fabricane was achieved in 20 steps for both azide and azide free approaches, and the key reactions involved in these reactions is zinc mediated Barnett bacillus reaction. So that mechanism I have shown you already, and another reaction is HWE reaction, okay. So this is very much interesting example how to start from D-glucose. As you can see, so this D-glucose, commercially available D-glucose, we have started, and we could go the long way to get this plus fabricane. Okay, and all reactions are successful enough this to give this natural product plus fabricane, right? Very interesting example. Yeah. Okay. So now we'll see another example of natural product, that is pheromone. Okay. So this is the raceme structure of plus minus racemic pheromone, and if you see, this is having only one chiral center. Okay. So this is the chiral center. Okay. So based on this, we can have both isomer plus and minus. So, and the name of this natural product is pheromone, and so this is the mealybug. Okay, so this is and paste for agriculture crops. So in 2009, basically in 2009, Miller group, they have isolated. So this is an sex pheromone, and this was isolated from the female long tailed. If you see the tail are long, okay, long tailed female mealybug, Pseudococcus longispinus. Okay, and this is an paste. Okay, for agricultural crops. Okay, so now the structure, if you see, it is having one total two quaternary centers. Along them, one is chiral center, and it is in monoterpene. Okay, so it is in monoterpenoid class of molecules. And now, if you see, it is produced in very limited quantities, a few micrograms. That means through natural source. Okay, through this, it is produced in very limited quantity. So that is very less. Also, the last bullet point, it is written there, key, a minimum dose of 25 microgram of racemic pheromone. So a minimum dose of this racemic pheromone about 25 microgram. So that is enough or sufficient to attract potential males for mating, and it can stay for more than 3 months. Okay. Anyway, we will not go to details of biology and all. So first we will see the for retrosynthetic analysis, how we can do the retrosynthetic, how we can plan for retrosynthetic analysis, and we will see some forward synthesis also. Okay. Yeah. So for this is a retrosynthetic approach slide. Here you can see that plus minus pheromone. So this we could get from this plus minus two. Okay. This is racemic synthesis. So this compound one we could get from compound two by basically by elimination of this acetate, right? We can get this olefin. Now this acetate, so this compound 2, how we can get from plus 3 by radical cyclization. Okay, so radical cyclization between this carbon and this carbon. Okay, so how much member ring will form? One, 2, 3, 4, 5. 5 member ring will form. So this carbon and this carbon radical cyclization will give this compound 2. And this 3 compound 3 we could get from 4 via Wittig olefination. Okay, at this carbon. Okay, Wittig olefination will give this product. Okay, any doubt? Anyway, this compound 4 we could get from 5 via this tarbish tarbutyl tarbutyl acetoacetate. Okay, tarbutyl acetoacetate we could get. So this is the commercially available compound. Okay, anyway, we will start from this compound 4. So this racemic 4 plus minus. So first Wittig reaction is happening. So this is the Wittig halide. In toluene reflux condition, we will get this carbon and this carbon. So this carbon and this carbon, CC double one product. Okay, so this plus minus 3. Now our main key reaction is radical cyclism reaction. Okay, that is iron ag. So iron 3 phenylsilane in ethanol. Okay, so radical cyclism reaction will happen between this carbon and this carbon. Okay, so it will give this two. So how it is happening, I'll show the mechanism as well. So basically, if you consider this iron 3 and phenylsilane, okay, it first radical anyway, radical will generate. So one electron. So this e, so it will come here and it will generate this tertiary radical. Sorry, yeah, tertiary radical. Okay. Now this tertiary radical, okay, so this tertiary radical, what will happen? So it will add to the beta carbon. So this beta carbon alpha beta unsaturated ester is electrophilic, right? So this radical will add to this electrophilic carbon and it will give this CC bond product. Okay, this cyclopentate. So now how this mechanism is exactly happening, I will show you. So we are using this iron ag. Okay, so this is the our catalyst Fe ag thrice. So basically phenylsilane also you are using and ethanol we are using. So here ethanol we are using. So this is alcohol and phenylsilane what will generate. So it will generate. So it will substitute one of the hydride from silane and that hydride will come to the metal center. Okay, iron 3. So it will generate basically this compound. Yeah, this catalyst. Now what will happen? So now this radical H dot, okay, H dot will add. Okay, so this will generate basically H dot. So this H dot will adds to this carbon. Okay, and it will generate this radical. Okay, so now after giving this H dot, it will give this. It will give back this iron 2 ligand. Now what will happen? So this radical and this electron withdrawing group. Here we are having this alpha beta unsaturated ester, right? In our compound, we are having this alpha beta unsaturated ester. That is intramolecular. That's why ring is forming. Okay, anyway. So basically, this radical will add to this beta carbon. So like this 56, it will add to this beta carbon and it will give this radical here. Okay, right? Okay, now after getting this radical, what will happen? So this iron 3 will donate another electron. So it will then donate another electron, E minus, and that E minus it will add to this radical. Okay, and it will so basically this carbon. So it will have now two electrons. So that means it is negative charge, and this negative charge We'll abstract proton from this ethanol, whatever protic solvent we are using, and it will give this product. Okay, CC bond. So basically, this CC bond is forming. Okay, and this methodology was first utilized by Professor Phil Warren, and they are published in Jack's paper. Okay, so this mechanism for the CC radical coupling, do you have any doubt? This mechanism, you can write in comment section. Okay, if you have any doubt about mechanism, you can write in comment section. We can discuss. Okay, so now come back to this again. This three, now we can convert to two via this radical CC coupling reaction. This C and this C coupling reaction, right? Yeah. So after getting this plus minus two, what we are doing, we are treating with this compound with lithium aluminum hydride. So this reducing agent. So what it will reduce? So basically, we are having this ester, right? We are having this ester. It will reduce this ester. Lithium aluminum hydride will reduce this ester, and it will give this primary alcohol, right? Any doubt up to this? Okay. After getting this alcohol, we are treating this compound 6 with acetic anhydride and DBN. DBN, as you see, I have written here the structure of DBN. So, like DBU, TBD, DBN is another base, bicyclic, this nitrogen containing base, so bulky base, non nucleophilic bases. So, DBN, what will happen? So, it will abstract proton from these two alcohol, but if we use one equivalent of acetic anhydride, right, so it will first this primary alcohol, whatever the sterically free alcohol is there, that will get acetate in presence of in this condition. Okay, and if we use two equivalent of acetic anhydride or more than, then both acetate will get. Okay, so on the next step, so this is the last step to get this plus minus pheromone. So what is this thiocarbonyl diimidazole? Okay, DMAP toluene 130 degrees centigrade 5 hour. So what will happen basically? So this alcohol. So this is the TCDI, thiocarbonyl diimidazole. So this alcohol will adds to this carbon sulfur, and it will fall again. It will return back and it will remove one of the imidazole. Okay. Alright, so basically this alcohol will form between this CS bond. Okay, so after this, what will happen? So what product it will get? So basically this oxygen, so this is sulfur, and this is the imidazole. One of the imidazole will be there. Now in toluene reflux condition, what will happen? This elimination, pyrolytic chain elimination will happen. Okay, so one of the proton it will abstract, and this C bond, CH bond will break, and this will give the CC bond, and this CO bond will break. Okay, and you will get ultimately this double one, and that is the plus minus pheromone, right? So any doubt in this slide? So if not, then it's good. So what is the conclusion? So the racemic and anesthetic selective synthesis of this long-tail mealybug pheromone were completed using an iron-mediated hydrogen atom transfer reaction as the key step. Okay, and this racemate was prepared via an acetoxidine with 5 steps and 37% overall yield. Okay, so that compound, so this was synthesized in 5 steps, one, two, three, four, five, and overall yield is 37%. Okay, so quite high yield because as you see the steps are less, so yield also get improved. Okay, 37% overall yield. So any doubt in this slide or today's section? So if not, then it's good. So today we'll stop here. So if you have any doubt, you can write. You can ask in comment section of YouTube videos as well. Okay, so we'll stop today. So have a good time. We'll see you later. Okay. Thank you for joining. Okay, I am leaving now.